Adam Schwaniger, and this is my Computer Science Foundation's presentation on the longest path problem. The longest path is, the goal is to find the longest simple path, which means you don't repeat any nodes or vertices, and you're finding a path from one node to another, ideally going through as many nodes without repeating as possible. The graph can be directed, undirected, weighted, or unweighted. The hardest part about this is the solution time grows exponentially long with the number of nodes and edges in the graph. Real-life applications of the longest path problem are seen in circuit design, so using that to model and optimize signal propagation and delays with circuits, project scheduling, and network routing. The approximation algorithm I picked was the ant colony optimization method. So it's inspired by the behavior of real ants, and they communicate through pheromones, which are chemicals they deposit on paths. And over time, the paths with more pheromones attract more ants, which reinforce the high-quality routes. So there are some steps that I've included here to how that is put into practice. So you can define the network as a graph. The nodes represent the locations and edges, represent the connections between them. So you initialize the pheromone levels on each edge, and as the ants start as a designated source node, then they move to neighboring nodes based on probability and pheromone level. They detect pheromone levels based on the length of the edge or the distance. And so as each ant completes its path, the pheromone levels are updated, and so they are going to be depositing more pheromones on the longer edges. And essentially this would be repeated for a certain amount of iterations, allowing the ants to progressively discover longer paths through the network. There is a quantum algorithm paper, and that is linked down here if you'd like to read that. But I did include the abstract from the paper, just saying they presented the quantum algorithm for the longest trail problem. It's to search the longest edge simple path for a graph with a certain amount of vertexes and edges. And the simple means no edge occurs in the path twice. Vertexes can occur several times, and their big O algorithm is O times 1.72m, which is the edges. So in summary, the long path problem is NP complete. Solutions are computationally expensive, meaning obviously long and challenging, and exponentially grow with the size of the graph. And there are some potential breakthroughs with the quantum computing prospects. I've also listed the references for the presentation down below.